Thanks for coming. I'm very excited. This is the first meeting for our little club, and I'm very proud of all the work that's gone into this. Thanks for coming. I've got a great presentation for you tonight, but before we start, I want to make sure, does everybody have a strip of paper? Everybody's got one? Yep. If you don't, ask Sue in the back, okay? That's going to be what we use tonight. And you need a pen. Got to have a pen. Good. I hope I'm going to teach you something that blows your mind tonight. Really, really exciting stuff. So, first, the Skywatchers Club is actually a club that was put together by a consortium of 4 different groups. The Foundation for Geauga Parks is a fundraising charitable organization. The Geauga Park District is active as well as the Burton Public Library and the Geauga Public Library, and my club, the Chagrin Valley Astronomical Society. Now, we put a lot of work into bringing together this project, including telescopes for borrowing it through the library system, and these kind of programs like this geared towards young people and young at heart. Kids and their families and anybody interested in astronomy. We welcome anybody. So what do we do at Geauga Skywatchers? Well, we explore astronomy. That's what we're going to be doing with various lectures and hands-on activities and introduction to scientific instruments and how to use them with the guidance of local experts. That's me and Marty back there. Sophisticated equipment available through my club or through Observatory Park, like that giant telescope. We have access to that in this club at Observatory Park. Our goal is to teach the wonders of the solar system and the universe and hone skills in science, technology, engineering, mathematics, reason, and critical thinking, and things like electricity and magnetism and anything that touches on the science and practice of astronomy. Our goal, our mission statement, if you will, is right here. We help make bright minds shine with the light of new knowledge. We inspire the next generation of working scientists in our communities. And our motto is, we look up. So, I'm George Trimble. I'm the president of the Chagrin Valley Astronomical Society. At the end, I'll introduce some other important folks that have helped make this all possible. But I'm going to be giving a talk today on the scale of the universe, really of the solar system, to get started. We're going to do what's called the folded solar system activity, and it's really neat. I hope you learn a lot. So, let's start at the beginning. The sun is the center of everything, at least within our solar system. So on your little piece of paper, okay, this will be your strip here of paper. In the left-hand corner, I want you to put a little mark that points to the corner and a little S for sun, okay? The sun is our star. When you look up at night and see the little twinkling stars, those are just like suns. If you get close to them, they look the same. Our sun is a star. And what's going to be way out here? It was recently demoted from a planet. Anybody know what that is? What?
Pluto.
Pluto, yes, very good. You're absolutely right. So we're going to have our solar system size bracketed between the sun and Pluto. The whole solar system shrunk down into your hands on this piece of paper. Did you put your little mark on there?
Yeah.
Sun, Pluto, perfect. Okay, everybody got that, right? So, Pluto is really, really far away. It's very cold. Here's a picture of Pluto. And notice here, what is this little spot? What is this? We're still trying to figure that out, but some people seem to think they see Pluto the dog in here. I have to stretch my imagination a little, but some people can see it. Okay. If you were standing on Pluto and looking back at the sun, it would look like a very cool, distant, cold object. Here's an artist rendition here of what the sun might look like from Pluto. Very far away, barely giving you enough heat. You would be an icicle or a popsicle on Pluto, okay? I'm serious, it's cold.
Not a very good popsicle.
And not a good tasting one, right? All right. So look, here's another picture. This is what the sun looks like in terms of its, we call it the angular diameter from different planets. From Pluto, the sun looks like just a little speck in the sky, hardly anything, so far away. Our sun looks like that. It subtends, if you will, about an angle of a half a degree in the sky from our vision. If you use a protractor, it looks like it covers half a degree. At Mercury, the sun looks considerably bigger because it's, of course, closer to the sun. All right. So now, what we're going to do is fold our paper in half. Bring the sun to meet Pluto and crease it. Crease your paper right in the middle, and there you'll make a little mark. Okay? And this is Uranus, one of the gas giants. That's the halfway mark. All right, now, before we get too much further, we're going to start laying in some numbers. That's U for Uranus. Who knows what an astronomical unit is? All right?
This is between the Earth and the Sun.
Yeah, it's the Earth-Sun distance. 1 AU. 1 AU is 93 million miles. 93 million miles. That's the distance between the Earth and the Sun. Earth isn't even on here yet. But I just want you to get a sense of how big the solar system is, because Pluto, and you can write this on your little paper, is 40 AU from the Sun. 40 AU. Astronomical units. So 40 Earth-Sun distances between there. And I'll tell you something, the Earth is really far away from the Sun. Now, how long does light take to travel from the Sun to Pluto? I'll tell you, it's this much, 5.5 light hours. Write that down, 40 AU and 5.5 light hours. Who knows what the speed of light is? I'll just say SOL, speed of light. You got it?
386,000 miles per hour.
So it's 3 times 10 to the 8th power meters per second. And I wrote down here because I can never remember, that's 670 million miles per hour. 670 million miles per hour. So here's a thing to think about. How many seconds does it take for me to snap my fingers? Just quick, right? A second. Pow. In 1 second, light can go around the Earth 7 times. Yeah. So every second, it can see China 7 times. That's how fast light goes. It's ridiculously fast. And so let's just think about that for a second. 7 times around the Earth in 1 second? How many times are there a second in an hour? How many seconds in an hour?
Okay, I need to do is
Just look at a clock. There's 60 little tick marks going around the clock, right? How many minutes in an hour?
60.
Oh, I should ask you the right question. I did it wrong, guys, didn't I? Boy, that was a tricky question. I'll give you. You were going to do the math that I couldn't. So, how many seconds in a minute?
60.
How many minutes in an hour?
60.
Good. How many hours in a day? 24. Right. How many days in a year?
360.
5 and a quarter. Yes. Good. 365 and a quarter. So imagine when you multiply all those numbers out, how many seconds are in a year or an hour or a day? It's an awful lot, right? And for every 1 second, light could go around the Earth 7 times. Imagine how many seconds can fit into 5.5 light hours. Okay, so that's an awful lot of travel time for light. So let's look here at Uranus here. So it's halfway between the Sun and Pluto. So how many astronomical units is it? It's 40 to Pluto, so it's got to be what to Uranus?
20.
Yeah, 20. So we'll put a little 20 under there, 20 AU. Mark that on your paper. And it's about half of this number. Now don't crack me on the skull if my numbers don't add up exactly, okay? I'm rounding and averaging a little bit because the fact is distances in the solar system aren't exact because our solar system isn't really perfectly comprised of circles. Everything, I should say, is going around in ellipses. And sometimes the ellipse is closer to the sun, and sometimes it's further from the sun. And so we're using average numbers here for these distances. You guys follow? All right. Now, if this distance here doesn't boggle your mind, 40 astronomical units, 5.5 light hours of travel time, then the next thing I'm going to tell you will boggle your mind. But first, let me ask you what this means. 5.5 light hours. The light's traveling for 5.5 hours to get to us. That means when it reaches our eye through the telescope, it's already 5 hours old. That light is already 5 hours old. That means that Pluto could have blown up and we could still be looking at it for 5 hours and wouldn't know it. There's a delay in information because of these vast distances. All right. So now I'm going to tell you something that's really going to make you crazy. So the nearest star, now we're just talking about planets. These are bodies that orbit our sun. But what about stars outside of our solar system or somewhere else in our galaxy or even in a different galaxy? Does anybody in here know? Let me see if this guy over here knows. Do you know the nearest star? Alpha? There it is. Okay, Alpha Centauri. Who's ever heard of Alpha Centauri? All right, good. Alpha Centauri, really I should say Proxima Centauri is the nearest star, and it's 4.35 light years, not hours, years away from Earth. So I did the math, so I'm going to save you the trouble. That's 38,132 light hours. In other words, it's just about, if you divide these two numbers, it's about 7,000 times further than Pluto. That's really, really far away. The nearest star. So, that's traveling at the speed of light. But don't lose hope. Don't lose hope. In another lecture you'll learn that Einstein gives us hope. You pick a star 1,000 light years away, and you tell me how fast you want to get there, and I'll tell you how fast you got to travel and not exceed the speed of light. Because distances shrink and time dilates when you go fast. So all of the universe is ours. We can get anywhere within our lifetime. Energy's the problem, though. That's the problem. But that's a different lecture. But don't give up hope. You can get out there if you get a fast enough ship, and it won't take you 3 light years, or I'm sorry, 4.3 light years. So that's also a little mind-boggling. Okay, so we've got Uranus on there. Who's ready for another one? All right, let's do this. Let's fold Pluto over to Uranus. Pluto to Uranus. Let's make a crease in our paper right in the middle. Now, is it a little bit strange or interesting or pique your interest or curiosity that somehow we're folding paper in half and the crease corresponds with a planet? There's got to be some weird mathematics behind that, right? That should be slightly startling to you, and yet it's true. So Neptune, let's put an N there. Okay, and this is going to be, write down, 30 astronomical units. If you go from the sun to the earth, you're only 1/30th the way to Neptune, and it's 4.1 light hours. Light hours. All right. Hello. All right, we're going to pause at Neptune. I want to do some cool stuff. Watch this. All right, buddy, can you work a calculator?
Yeah.
All right, I knew you could. I'm
No
just
pressure.
asking. No pressure. All right, I'll tell you when here in a second, okay? Neptune, get your fingers ready. 2,700,000,000 miles away. Miles away. 2,700,000,000. That should pretty much fill up the screen, okay? With all those zeros.
No, you missed the 2.
Okay, while you're working on that, let me tell you how wide across Neptune is. It has a diameter. Do you know what a diameter is? That's the distance from one side of the circle to the other side. What do you call it? One side of the circle to the middle. Radius. Who said it? Right on. All right, so the diameter of Neptune is 30,599 miles. All right. So you got that big number in there, that first one?
Yeah.
Right on. Now hit divided by, and then type in that number, 30,599, all together. What do you come up with?
I think it's 8,823,000,000.
You got it. I'm going to write it down. It's 88,238, and there's probably a 0.17, right? Okay. So this is the ratio. What do I mean by ratio? It's just how many of these diameters of Neptune will fit between the sun and Neptune. You'd need that many Neptunes to walk from here to Neptune, or from the sun to Neptune. Our little distance, we're so close to the sun, and doesn't even matter. We don't have to even take that into account. But that's how many Neptunes you'd have to take, stacked right next to each other, lined up, to get from the sun to Neptune if you wanted to walk all the way there. That ratio is going to be important. We're going to use it, okay? Now, well, where'd it go? Oh, here's Neptune. It was hiding from me. Okay, so a quarter. Give me a guess. How big is a quarter? Yeah, about an inch. Is that what you're saying? Does an inch look about right to you? Okay, a quarter of an inch. I'll tell you, it's this much right here. It's 0.955 inches. So you guys are right in the right ballpark, okay? Now, You're going to be my little helper, okay? You're going to take my quarter, and since you're helping me, you get to keep it, all right? You guys see that little BB? You see that little BB right there in my hand? We're going to let that be Earth, okay? And we're going to set that BB right here. Is it going to stay? Okay, good. Now, how far do you think you got to move that quarter, if that's Neptune? How far away from the Earth? Come on up here. Now, you know Neptune's bigger than the Earth, right? So how far away does it have to be about the right scale for the real thing? Do you think it's that far? If you're in a little spaceship, is that as far as you got to go?
No.
How far do you think? Just walk away, and you stop when you think it's about the right distance, okay? Okay? Let's see how far she goes. You guys can yell out stop if you think she's going too far. How about right there?
She's going to keep walking.
Yeah, okay. Stop right there. Is that too far, do you think? No, it's not too far? You think it's farther? I'll tell you what. Let's use the power. Come on back. Keep the quarter. You can't walk far enough, I'll tell you that. We're going to use the power of mathematical thinking to calculate how far this would have to be, just to get a sense. I know you. Hi there. Just to get a sense of how big the solar system is, okay? So, who can I pick on? How many eggs in a dozen is what I want to ask. How many eggs in a dozen?
12.
Yes, good. How many eggs in 2 dozen?
24.
Good. Okay, so how did you do that? You did it in your head, but I'm going to show you how you can do it very organized, because pretty soon it's going to get complicated and you're not going to be able to do it in your head. But I'm going to show you the tools you need to solve this problem. Okay? So we said I'm going to do green here. What can I erase? I'm going to erase this up here. Okay, so we said that there's 12 eggs in 1 dozen, right? Can I also say there's 1 dozen in 12 eggs? Doesn't matter how you say it, right? Doesn't matter. So if I say 24 eggs, I'm going to show you a little trick. I just have to pick whichever one of these is going to do us a little favor. And I'll tell you why. It's going to be this one right here. Because this is 24 eggs, and we're going to multiply it by 1 dozen over 12 eggs. And why did I choose that one? Well, you guys know when you have a fraction, whatever's on top, if it's the same on the bottom, you can cancel them out, right? What's 5 divided by 5?
1.
What's A divided by A? 1. What's 3 divided by 3? 1. Yes. Anything over the same thing is 1. We chose this ratio here because eggs is on bottom. Eggs cancels. So we say 24 times 1 divided by 12. That's 2 dozen eggs. Our answer, the units is in dozen. You see, we keep our units here, dozen. So 24 divided by 12, and it tells us what the answer is in units. This is called dimensional analysis. I don't care if you forget about it when you leave here, but you'll run into it again, and it can be really, really handy. Now, I should have had a little tissue or something, but I didn't. All right, so let's set up. Our question is how far away does the quarter have to be when we know the size of the quarter and we know the ratio that we already calculated is this magic number right here, right? So we have the distance away, we don't know, we're going to call it x, But we know this, thank you. But we know the size of the quarter is 0.955 inches. So we know that has to equal 88,238.17, okay? So can we do a little algebra to isolate the x? Not everybody will understand this, but it's okay. We'll just multiply both sides by 0.95, and that cancels. And we multiply this side by 0.95. And what we get is x equals that times that. Can you do that for me? It's this number, 88,238 times 0.955. It's going to be a big number. What do you got? You want me to read it?
Yeah, it's 84,267.
You're right. 84,000. You keep going. You're doing great. 84,000 inches. Well, that doesn't help us much. That's why I'm interested in talking to you about eggs. Can we turn that into miles? We can. So we're going to do like this. We're not going to actually do the math. I'm just going to set up the problem so you see how we solve problems in science. Okay? All right, so we've got 84,000.
267.
0.29.
Okay. Inches, and we have to, so this is inches, IN. We have to have some inches to centimeters, and then centimeters to meters, and then meters to kilometers, and then one more, kilometers to miles. And then watch, inches cancels, centimeters cancels, meters cancels, kilometers cancels, and you're left with miles. All you need to know is how many centimeters in an inch. Well, it's 2.54. I've got that memorized. How many meters in a centimeter, or centimeters in a meter? And that's goes like this: 1 times 10 to the minus 2, which is really 1. Move the decimal place back like that. Okay, and then 1 times 10 to the 3. You don't have to know these numbers. You just know how to set up so the units cancel. So I did the math. Okay, 1.329 miles. Hey, young lady, you got your tenny runners on? You got a long way to go to take that quarter, 1 1/3 mile. So I actually did a map to figure out. This is us, Chagrin Public Library. You go down here, take a right, go out to Sage's Apples.
You might need to come in your car.
Yeah, I think so. You're almost to Auburn Road.
Oh, wow.
If you put that quarter there and then get your eagle eyes on, do you think you could even see it?
No.
Yeah, but that would be about how Neptune looks from Earth to your naked eyes. So, stand up for me, buddy. So, we called this his angular diameter. The angle my arms make is his angular diameter. Now run to the back. Run, go. As he goes away, his angular diameter gets smaller and smaller and smaller. See, I can barely fit him between that. Come on back. As things get further away, their angular diameter shrinks and they pinch out of sight. And that's why we need telescopes like this one to see them. Telescopes magnify a little bit, but they also brighten an image too. We'll learn about telescopes. Marty Mullet back there, he's going to teach us about telescopes at one of these future events. So, Sage's Apples. That's how far that quarter would have to be to have the same angular diameter as compared to this BB being Earth as Neptune does to the real Earth. That's a really, really long way away. Because look, that's not even close to the real Earth size. Okay, all right. Okay, let's fold some more, shall we? Saturn. We're still in the gas giants, guys. We haven't even gotten to the rocky stuff. What kind of planets have you got on you? You got it. Look at her dress. She's ready. She's dressed for the occasion. I love it. Okay, so fold your paper from the sun to Uranus, and that'll put you at a halfway mark right in here, and you put an S there, and that is Saturn. Any guesses? If Uranus is 20 AU, what's half of 20? All right. And then how many light? Now we've gone from light hours. Now Saturn, I should say Uranus was 2.6 light hours. We're getting down to where we're almost going to dip below the hour mark. We're at 1.3 light hours at Saturn. 1.3 light hours. It still takes light. Now tonight, listen to this. Tonight we're going to have telescopes set outside in the parking lot, the library parking lot. And if the air is clear, just maybe we'll take a peek at Jupiter or Saturn. Marty, is Saturn available around the time? Okay, good. Maybe, just maybe, you'll see the rings of Saturn.
I've seen Saturn before when we went stargazing at Observatory Smart.
You've seen it before. Did you see the rings?
I forget.
Okay, well, this time remember, you're going to see the rings, I hope, and hopefully you see some moons. The moons, Saturn kind of looks like this through a telescope, right? And look for little moons lined up all around Saturn. It's easier even to see around Jupiter. Those look like stars, but they're lined up and they're going around and around, and you can actually see the moons of these faraway places through a telescope. I hope you see it tonight. And remember that the light coming from Saturn took over an hour to get to your eyes, an hour and 20 minutes. That's old light. It's ridiculous. That's very far
You're
away.
just like, oh, there's Saturn. Oh wait, no, it's actually going to be over there right now.
Yeah, it's already moved by the time you see it, right? All right. So let's fold your paper in half yet again. What's next, guys? Wait a minute. What's next, buddy? What's the next planet? Yes, Jupiter. You got it? So you're going to fold from the sun over here. Oh, it's a little dark over here, isn't it? To Saturn. So let's cast a little light on the subject. Sorry, guys. Is that a little better? I blinded everybody. Okay. So Jupiter. Now we're at Jupiter. We're going to fold from Sun over here over to Saturn, and Jupiter will be the crease.
Thank you very much.
Everybody got that? The Sun meets Saturn, and the crease is Jupiter. That's 5 astronomical units away. 43 minutes, 43 light minutes, 43 minutes of travel time for light to get to your eye from Jupiter. This is also a gas giant. You couldn't stand on the surface. There's no surface.
When are we going to get to the actual hard stuff?
The hard stuff?
Yeah.
Oh, well, okay.
These gas giants.
Oh, you mean the hard rocky planets. I gotcha. I thought he was testing me. Like, this is too simple for me. The hard stuff. All right. Notice we're already here, and this is Jupiter, and we haven't even gotten into the inner planets. Where's the room for Earth and Venus and Mercury? Where's it going to be room? We're running out of room. Keep folding. Yeah. All right. So, everybody wrote down 5 astronomical units, 5 times the distance from the sun to the earth, and 43 light minutes. Let's fold again. Sun to Jupiter. Now things are getting really tiny. You get to practice your origami skills. Okay, trick question. Now let's see who's really, really sharp about the solar system. What is going to be here? Yes, somebody said it. What are you going to say? Close. You're very close, but I told you it was a trick question, so I tricked you. What about you?
The Earth?
Nope, it's not a planet.
The asteroid belt.
You got it. All right. So what the heck is the asteroid belt? Huh? What is it?
It's a asteroid that separates the outer planets from the inner.
There you go. There you go. So that's a great answer. You know, the fact is that the asteroid belt was a planet that could have been. It was a baby planet in the works, but it never formed. All that dust and all those asteroids and thousands of particles of stuff floating around in this belt around the sun has been prevented by forming a planet, in part because of the perturbing influence, the gravity, the powerful gravity of this planet right here, Jupiter. Jupiter is so massive. In fact, a guy once said that the solar system is comprised of the sun, Jupiter, and a bunch of rubble. All the other stuff is so small compared to Jupiter. The Earth would fit into a little circle like this. That's how small the Earth is compared to Jupiter. So it's really true. It's mostly the mass in our solar system is comprised of the sun and Jupiter and a bunch of other junk. So because Jupiter has such a tugging force on this area of our solar system, these little particles couldn't gather together and start making little planetoids and planetesimals and form into a proper planet. And so forever they're just scattered as dust, asteroids and chunks. Marty, what's the biggest, what are a couple big items in there? Is it Ceres? Vesta? Okay. So, thank you. All right, so mark the asteroid belt. That's halfway between the sun and Jupiter's mark, so I'll put that right here. Okay, so that's the asteroid belt. Okay, now we're 2.5 astronomical units away.
I thought Earth was 3 point something.
Earth's one by definition.
Oh,
Yeah, sun to the earth is 1 astronomical unit. Now I'm going to change to red because we're getting kind of close over there. Okay, so let's fold again. We're going to fold from the sun to the asteroid belt and then open it up, and right at that crease. Now someone back here had the right answer. You, sir, had the right answer last time. What is it? Yes, sir. Give me 5. Right on. Okay, so mark Earth. We finally found our home. Right there. Now I hear grumbling. I hear some grumbling. Huh? I know. I knew there's always some smarty in the audience that's keeping track of the numbers. Thank you for that. Remember I talked to you down here about how I'm going to have to round because these are not based on perfect circles. They're averages based on elliptical orbits. And because we are folding and exactly halving, it's really not exactly just that. This gets it pretty darn close though. So it should be 1 astronomical unit. But as you say, if this was 2.5, that would have to be 1.25, right? Well, we're cheating a little bit. Thank you for pointing it out, though. So, round numbers, fuzzy numbers. So that's Earth. And how far away is Earth from the sun in light time? Anybody know? Third? Oh, you got the right answer to a different question. Let me ask you the right question. I made a mistake. I'm sorry. What number planet is Earth from the sun? Yeah! Give me 5. Good answer. Good answer. Third rock from the sun, right? Okay, so another different question. How long does it take light to get from the sun to the Earth? Yeah. Yes, 8 minutes, 8 minutes. Everybody seems to know that. Good. So I have written down here 8.3 light minutes. And you're right, because it's an ellipse somewhere on there. It's probably exactly right. You got the right answer. So 8 light minutes away. So even light from the sun, our heat, our energy source, ultimately what drives all of life on Earth, is 8 minutes away. The light you see from the sun is 8 minutes old when it hits your eyes. And don't look at the sun, right? It'll burn your eyes. I'm a doctor, so I got to say that. All right, so any other complaints so far? Let's see, we did what?
You skipped the planet.
Ah, thank you. Go ahead. Which one?
Mars.
Anybody else see that? We missed Mars, right? All right. This is where the rule kind of breaks down. I don't know what's going on here, but I'm going to tell you, to get Mars, we got to fold Earth to the asteroid belt. So move the asteroid belt, or the Earth to the asteroid belt right here, right there, and in between we put Mars. That's a rule breaker right there. Mars, the red planet, the bad boy, breaking the rules. It's right in the middle between the Earth and the asteroid belt, right? All right, that's where Marvin the Martian lives. That's 1.8, so write 1.8 astronomical units. It's about 12 and a half light minutes away. Now just look at that, just for a second. Look at this. We got this whole sheet of paper, and if all we were interested is the Earth and the sun, we could just cut it off right over here and throw all the rest away. That's all we need, this little tiny piece of paper. And so you think it's far to get to the sun, and it is. And yet, look how much further it is to get to Pluto. Yeah. All right, so let's do 2 more folds, right? Let's fold the sun to the Earth. Let me get caught up here. Oh, there's a little asteroid for a little asteroid astronomer back there. There's the Earth. Oh, now. So we fold the sun to the Earth, and right in between, in the middle, is what? Venus. Now, who knows what Venus, the planet, is named after? Oh, yeah, very good. Beautiful, right? She's supposed to be beautiful. But look at this. Does this look like a beautiful planet? No. It's all hot.
If you're a lava monster.
If you're a lava monster, yeah, for sure. But this is definitely not a beautiful place to visit. Marty, correct me if I'm wrong. Didn't the Russians send a probe on? It was the Russians, right? And I think it got eat up by sulfuric acid within a few hours or minutes or something. It rains acid. That's cool.
Hey, look, we're almost there.
Gone. Okay. So that's Venus. Not so beautiful after all. Runaway greenhouse gas. Runaway CO2. Hot, hot, hot. Environment out of control. You couldn't grow a plant there.
You couldn't even live there. You'd probably melt.
You would melt. Yeah. And you think that's hot. Let's go in one more, okay? Shall we go in for our next and last planet?
How far away is it?
Oh, I'm glad you're keeping track. So it's 0.6 astronomical units. That's about 60% of the distance from Earth to Sun, right? 0.6 is 60%. And it takes light 6 minutes. It's that close to the sun, and still 6 minutes for light to get that far. Crazy. All right, so you guys know how to do the next fold, the last fold, right? See if you can do it. My fingers, I had to have my kid do this because my fingers were too big. Huh?
You expect us to do this?
I know, it's crazy, isn't it? I had to have my son with his little tiny fingers do this.
I did it.
You got it? Right on. You get it? Does yours look like this tiny little flap like that? Yeah, it's ridiculous. Well, so at that little crease you put mercury, right?
What happens if it's behind my son?
What's that? I can't even fit that stuff in there. What?
It's right on top of my son.
Yeah, you're just going to have to squeeze it in. It's getting close. They're kissing. So mercury is 0.3. It's only a third of an astronomical unit, 30%. And that's 3.2 light minutes. Now remember, light goes around the Earth 7 times in 1 second, times 60 seconds, times 3.2. That's how many times around the Earth light would go to get to Mercury. It's still a long way away. It's not swimming distance. All right. So, does that kind of impress you a little bit? That all the stuff we know is crowded down on this end? Yeah. So now, all right, somebody was kind enough to bring this to me. Thank you so much, because this was going to get messy. I want you to look at the ink line you drew for Earth's crease. You see that line? On that line exists everything you ever knew, everybody you ever met, all of history. Let's zoom in with a magnifying glass on that line. That line you drew, we zoom in. I want you to know that the Earth and the Moon are like that on that line.
I don't see it.
What's that?
I can't see them.
I know.
Mostly because I'm all the way back here.
Your pen, the ink on your pen is too fat. It doesn't let us fit a moon in. Okay? So, all right, who else knows how to use a calculator in here? Let me get somebody. I'm going to pick you this time. All right, thank you for helping. Okay, there you go, sorry. All right, so now work with me here because we're going to use kind of fuzzy numbers again. We're just going to round a lot. But I want you to know that the distance from the surface of the Earth to the Moon is 240,000 miles. Okay? Turns out that that's about 30 Earth diameters. We can draw in here about 30 Earths, and that'll get us to the surface of the Moon. It's 30 Earths away. Most times, there's Mercury, by the way. It's cool. Look at that.
That's cool. Oh, that's cool.
Yeah. False color image. It looks terrible, doesn't it? And then we backed up to get Mars. Remember that? We had to back up on that one. Most pictures will draw the Earth, and then you see the Moon like that, right? But this is the real relationship. That's the Moon way out there. Can you imagine the spaceship going from all the... I get sick just going from here to visit relatives in Canada, let alone all the way up here. I get sick of driving. All right. So, let's do this. You got your calculator ready?
Yep.
We said that there's 30 Earth diameters, right? Okay, 30 divided by 2 is what? You can yell them out, but they're going to get harder here in a minute. Yep. Okay, so here's 15. Let me get rid of this. Now 15 divided by 2.
7.5.
Yes, ma'am. Thank you. 7.5 divided by 2 is what?
3.75.
3.75. Okay. 3.75 divided by 2 is what?
1.875.
1.875. Okay, 1.875 divided by 2. I know, you're bored.
0.9375.
0.9375 done. All right, will you allow me this little cheat? Is 0.9, that's 94% almost. Can I just call that, is it okay? Can I round and call it 1? All right, that's close enough to 1, isn't it? So, how many times did we divide 1, 2, 3, 4? Well, did we? Wait a sec, I missed one somewhere. We had 30, so I should say 30 up here divided by 2. So there's 5 divisions, okay, to get down to 1. And what does that 1 represent? Represents 1 what? Earth. You're close. You're thinking right. And that's important. So if we get 5 divisions of the total, we'll get the size of the Earth. And guess what? You already did that work on the other side of the paper. When we turn your paper over, okay, now we're going to let one side of your paper, now you were on the blank side, we're going to let one side of your paper be the Earth's surface and the other side be the Moon's surface. And guess what? If you count the 5th fold, okay, where it says Earth, you marked it Earth on the other side. On the other side, there's a fold that you labeled E for Earth. When you turn over, that same fold represents 1 Earth. No. Yes, 1 Earth diameter. Okay. Now what did I call these before? Moons or Earths? Good. I thought I made a mistake. All right. I did call them Earths. They are. So 30 Earths. So now you've identified how big Earth looks on this scale, and you could just draw 30 of those across the paper, and that's how far away the Moon is. And just keep in mind, if you cut the Earth in half and cut it in half again, you could draw a little moon. It's about a quarter of the Earth's diameter. So the Earth on this side right there, and the Moon here, little quarter size. See? So we said get rid of some of this stuff. So did you draw a little Earth in between the Earth fold and the edge of the paper? Did you do it? Let me show you mine. See, here's the Earth fold on the other side, right there. And I could fit 1 circle of Earth between the edge of the paper and that fold on the other side. Okay? Just to give you a sense of, if that's the size of the Earth, right there, and the Moon is a quarter of it, that's how far away it would be. Really far away. So on this side is the Earth fold, and we said it's 1.2 AU. Who was it that caught me? That was you. And on this side, it turns out that same fold gives us the diameter of the Earth. It's kind of cool. It fits between the edge of the paper and that fold. Some strange math keeps popping up in this. And then if you put a circle a quarter of the size of the Earth over at the other end, now you've got the proper ratio of them. Okay? All right. Now, let's do some cool... I like to work math in if it's going to add something interesting from time to time. And math is nothing to be afraid of because it's powerful. So we said that the Earth is 240,000 miles away from the moon. So my question is, how long would it take going 60 miles an hour to get there? Who's got that calculator? You want to do some work? So let's talk about the strategy. How are we going to do it?
240,000
Divided by
divided
60 miles an hour is how fast I want to go, right? So you're right. You just divide those two. Okay?
I already know the answer too.
You know the answer to that?
Yeah, 80,000.
You sure? When kids tell me an answer like that and I have a different one, I'm willing to assume they're right. I must have made a mistake. 4,000 is the answer. Okay. So if Grandma lived on the moon, it's only 4,000 hours to her house if you don't want to break the speed limit, right?
Yeah. And that's also if you can keep up with the moon, because it's always moving.
Did you come up with that answer on the calculator? Well, you got the answer in there still, don't you? Well, let me ask you, how many days would this take? 4,000 hours. How many days is that? Can anybody tell me the strategy? I heard it. What was it? Yes. Divided by 24. 4,000 divided by 24. What have we got?
666,666,667.
Okay, let me show you a little trick in math. 166.6, then we just put a bar over it. And that means it goes on forever. 6666666 and it repeats. Okay, that's what that bar means if you see it in a textbook. So 166 days. Well, how many years is that? How do we get that? Ooh, can we use dimensional analysis again? 166.6 days. Now, remember, we need a conversion factor, guys. What are the days to years? So there's 365.25 days in 1 year. Days per year. But that's not going to be useful because day is on top and year is on bottom. So what we need is the other relationship with year on top and 365.25. Can't I say that too? 1 year has 365.25 days. I chose that form of the ratio because days is on bottom, days is on top. These cancel, and I know I'm going to get the right answer by multiplying by 1 and dividing by that. So it's your number's 166.6 divided by 365.25. Okay, 0.456 years. Can't we just call that 0.5 and be done? That's a half a year. At 60 miles an hour, a half a year. Yeah, Grandma, we're going to have to email because I'm not going. Okay, so that's just under 6 months, right? So let's ask this question another way. How fast would we have to go? How fast would we have to go if we wanted to do the whole trip in 3 days? Because that's how fast the astronauts got there when they went to the moon. They did it in 3 days.
3,600 miles per hour.
Say again?
3,600 miles per hour.
Pretty close. I come up with 240,000 divided by 72 hours. Isn't 72 hours 3 days? 24 hours, 48 hours, 72. All right. So let's get our little calculator out. What's 240,000 miles divided by 72 hours?
Divided by
72. It's a lot of threes, right? It's 4 threes and then more threes. 0.3. Can I just put that bar on top?
Yeah.
It's a point. So it's 3,333 miles per hour. Have you ever gone that fast? I know it. I know it. But you are going that fast. The Earth is turning, and it's going around the sun. And the sun itself is going around the center of our galaxy. Somewhere towards Sagittarius, there's a black hole we're going around.
Yeah.
And we're going faster than that. So you're going that fast right now, at least. All right. So, and keep in mind that this distance that we're talking about, you got to go 3,000 miles an hour. And it still takes you 3 days. That's just to get to the moon. And that's the farthest we've been. And look at your paper on the other side. We haven't even got off our line. No human has been off our line, the little mark that says Earth. All that. So, this is a photo of Saturn. That's Saturn. You see the planet is in black in the upper left-hand corner, and there's the rings going around it. The Voyager spacecraft zipped past Saturn going this way, going 36,000 miles an hour, close thereabouts, I can't remember. And it turned around, and it looked back. And does anybody see Earth? A pale blue dot right here? That's us. And everything you ever knew, every nation, all right there. I'd like you to listen for a moment, if you could. Listen with me here to Carl Sagan.
The Voyagers were guaranteed to work only until the Saturn encounter. I thought it might be a good idea, just after Saturn, to have them take one last glance homeward. From Saturn, I knew the Earth would appear too small for Voyager to make out in detail. Our planet would be just a point of light, a lone pixel, hardly distinguishable from the many other points of light Voyager would see, nearby planets, far-off suns. But precisely because of the obscurity of our world thus revealed, such a picture might be worth having. While almost everyone has thought that the Earth is a sphere, and all of us somehow glued to it by gravity, the reality of our circumstance did not really begin to sink in until the famous frame-filling Apollo photograph of the whole Earth, the one taken by the Apollo 17 astronauts on the last journey of humans to the moon. It seemed to me that another picture of the Earth, this one taken from 100,000 times farther away, might help in the continuing process of revealing to ourselves our true circumstance and condition. It had been well understood by the scientists and philosophers of classical antiquity that the Earth was a mere point in a vast, encompassing cosmos. But no one had ever seen it as such. Consider again that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering. Thousands of continent religions, ideologies, and economic doctrine. Every hunter and forager, every hero and coward, every creator and destroyer of civilization. Every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there. and the mote of dust suspended in the sunbeam. The Earth is a very small stage in a vast cosmic arena. Think of the rivers of blood spilled by all those generals and emperors, so that in glory and triumph they could become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatred. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe, are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species can migrate. Visit? Yes. Settle? Not yet. Like it or not, for the moment, the Earth is where we make our stand. It has been said that astronomy is a humbling and character-building experiment. There is perhaps no better demonstration of the folly of human conceits than this distant human of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the painful dart, the only home we've ever known.
I think that's beautiful. Carl Sagan, I miss that guy. But those are his words. And I think it helps bring into perspective what that little tiny dot means, much as we're trying to seek perspective today to understand how big just our solar system is. And I hope that you join me each month for new explorations to explore how big the universe is, or how light behaves and things behave when they go fast. We'll talk about things like sundials and astrolabes. We'll talk about ancient ruins and structures that were used for astronomical alignments and things to determine when crops should be planted or harvested. We'll talk about the history of astronomy and cool personalities along the way. Now, we've made this group that I told you about. These folks here have actually purchased telescopes to go in all the libraries in this county. Thanks to the contributions of the Foundation for Geauga Parks and the work of these other groups, you can now take a telescope out on loan and take it home. And we'll teach you, the adults probably, or maybe they don't, but if you don't know how to use one, we're the place. We'll help you, and we'll introduce you to this telescope and many others, including the giant telescope at Observatory Park, and perhaps our telescopes at the Chagrin Valley Astronomical Society. Make sure to look at the books at the back there from the library. Maybe take one home tonight, a book about the moon or the stars. Your library is a great source of information and knowledge. And as you flip through those pages, your imagination can run wild. And you can come to me next time and ask questions. So ask your librarian about borrowing a telescope. And if you want to keep up with when our next meeting is and what the topic is, and you want to register for it, go to meetup.com. We're on there. Look for the Skywatchers. You can register on there, and you get all the emails and the latest updates. Once I actually sent out a coded message that you had to use a a frame shift code cipher to decipher. I play little games with you to make it interesting so you can figure out where we're going to meet next. Things like that, okay? There's our telescope. And then our next event is October 7th at 6:30 p.m. at the Bainbridge Library. And we're going to talk about sundials, how to tell time from the sun. But to do that, you need to know a little something about latitude and something called the equation of time. And what is daylight savings time anyway? And Eastern Standard. And how is that different from local apparent time? And what is a mean time? If you don't know what that is, and many, many people don't, this is the lecture to come to, and this one's fun. November 4th at Geauga West Library. We're going to talk about telescopes, all the way from the first one invented by Galileo to modern designs like Chagrin, how to use them and where the magic is. Here's a few people that deserve thanks for helping make this day possible. And Jeff, I'm sorry, Jeff Hyde should be on this list, and I failed to put your name on there, Jeff. I threw it in here at the last minute. I'm sorry. Raise your hand if you would, please. That's Jeff Hyde. He works for the Foundation for Geauga Parks. And it's his efforts, as well as Heidi and Sue Lundstrom back there in the back. Raise your hands. Those folks raised all the money to make this possible. So thank you all, really. And thank you to Chris Carroll, Alicia, and Amber, if she's sitting in here. These are your librarians. They've made this all possible as well. Ask them about telescopes and get some books. Are there any questions?
You even want your calculator back?
You like it that much? I'll take it back. Thank you. And thank you for your help, everybody. Now, we've got some telescopes outside. We're going to try to look at some cool stuff like the moon and maybe Jupiter and Saturn. So if there's no clouds, hang out. What you got? Do you learn anything?
I feel small now.
Yeah, me too. That's, yeah. Thank you.